if A is outputting a 0 and C here is outputting a 1, then we're getting a 1 and a 0 both output onto this same line at the same time. And then it's not clear what the inputs are going to be. So to really understand better, what's happening when we have all of these outputs connected essentially together in this way, it's useful to look at the actual output stage of a gate, because ultimately these connections are coming out of logic gates, right? Because whatever's going on inside here is just a bunch of logic gates. So if we were to look inside a typical logic gate, there would be some series of transistors and things that kind of do whatever logic operation that the logic gate is supposed to do, whether it's the AND gate or whatever. But then there's typically an output stage that looks something like this in front of the actual output of a logic gate. And usually there's these two transistors. And if this top transistor is turned on, then current can flow from the voltage source through and to the output. And so essentially the gate can be sourcing current that goes out the output. And that's typically what it does when the output is a 1 or when the output is on. Alternatively, this transistor could be off and this transistor here could be on, and you can think of it as connecting the output to ground, or you can think of it as the output is able to sink current, and that represents sort of the 0 state of the output. So another way to look at that is like this, where when the gate is on, there's this resistor that essentially connects you to the output. So sort of a resistor goes to the output. And then on the input here, what that means is that current can flow out of this output and then to ground in the next gate. And so current flowing this direction is seen as a 1. Alternatively, if the bottom transistor is turned on, then we have this scenario here where current can be sunk essentially into that output to ground. And when current is flowing this way, we consider that a 0. So if we come back to this bus, essentially when these outputs, if A is outputting some pattern 0 1 0 1 0 1, for example, really what it's doing is it's saying, okay, this pin is going to sink current, this pin is going to source current, this pin is going to sink current, this is going to source current, and so on an input, you're going to see current going one way or the other, and that's how the input is going to determine whether it's a 1 or a 0. And so essentially current will be flowing this way, or current will be flowing this way. And that's fine until you have two things trying to output at the same time. So if for example you said, okay, well C is not going to output anything, so it'll set all these to 0. Well, that's no good, because what that means, if you're setting all of these to 0, that means that it's going to sink current, and so if you have a 1 here, you're actually going to get current flowing out here and into the output here. That's not really what you want. You really want these to be essentially disconnected. And so there's a way to do that, where this gate, rather than turning on this transistor to output a 1 or this transistor to output a 0, if you don't turn on either transistor, then the output is not going to source current or sink current. And so essentially you're not going to get a 0 or a 1. You're just going to kind of have this output disconnected almost. And if you didn't understand anything that I just said in terms of sourcing or sinking current, that's okay. A better way, or maybe a simpler way, or a sufficient way to think of this is you can think of a gate in this way. So instead of thinking in terms of what transistors are turning on and off, if you think of it like this, where you have an input coming in, and this is just a simple buffer, whatever the input is, the output's going to be. The input you can think of as just controlling a switch. And so if the input is a 1, then the switch is up in this position and you get 5 volts coming out. If the input's a 0, then the switch is down in this position and you have essentially your output connected to ground. So you could sink current, or you could just think of it as the output is at 0 volts. But what we could do is to sort of, as an easier way to think of this scenario where both of these transistors are off, we could think of having an enable input. And if this enable input is a 1, then it kind of closes this switch. It connects the output. And if the enable input is a 0, or if it's off, then we can think of this switch as being open, and we can think of the output as being completely disconnected. And that's what we want, is we want these outputs, if this particular register is not enabled, we want those outputs to be disconnected. We don't want them impacting, some other data that's being transferred on the bus. And so, fortunately, they make gates like this. They're called tri-state gates, or typically called tri-state gates because they have 3 output states. There's a 0 or a 1 or a disabled or a sort of a not connected. Sometimes you'll see it referred to as high impedance or high Z or something like that. But basically this is considered a 3-state gate. And this is a pretty common symbol for such a thing. You have an input, this is a buffer, just an input and an output, but then you have this enable coming in the side here. And so an example of this that we'll use in our registers is the 74LS245. And you can see it's got a bunch of these gates in here, but what you should notice here is you can see you have an input that comes in, and then you have an output that goes out, just like any buffer. But you have this third enable pin, and it goes over here. There's a little bit of logic here, but essentially you have an enable input that's this E input that enables this thing. And so by using this tri-state logic, it gets us essentially what we want. It gets us the ability to have this enable line for each of these modules that's connected to our bus, and we can have that enable line low for all but one of these. And as long as it's low for all of them except for one of them, as long as only one of them is enabled, then there's only one thing that's going to be outputting either zeros or ones to our bus. And so we won't have any conflicts on the bus. And then when some other module then reads the data on the bus, you're going to be getting the data from the one module that's outputting that data to the bus. So I know that's a ton of theory, and it's okay if you didn't catch all of it. But the important part here is this notion of a bus and how that works and how that gives us the flexibility to add lots and lots of different modules, and how when modules are connected to a bus like this, any module can talk to any other module. And then as we start to look in the next videos to build one of these registers, and a register is just going to be able to store data that comes in and be able to put that data back on the bus. It's important just to understand how this works and understand that, okay, this thing is going to connect to a bus. It's going to have data could be coming from the bus, or data could be going to the bus, either way. And that's controlled by these control pins that come in, or these control lines that are going to come in from somewhere. We haven't talked about where those come from or how the computer knows when to turn those on and off. So if that's a little bit of a mystery to you, that's fine. We'll get there. But essentially we have an enable control line that says whenever that enable is high, then the data that's stored in here should be output to the bus. And of course we have to make sure that only one of those enables is high at any point in time, but we'll get to that later. And then there's also a load signal, and when that load line goes high, then what that means is that on the next clock pulse, we have a clock input here, on the next clock pulse, it should read whatever's on the bus and then store that in the register. And so in the next video, we'll actually look in more detail about what goes on inside this register and how to build one. So in the last video, we looked at the concept of a bus and how we can use a bus, which is this set of 8 wires, in this case 8 wires, connecting multiple different modules together, and how the bus provides a way for any module to communicate with any other module. So in this video, what I want to look at is actually what it takes to build one of these registers. In this case, we'll look at a register. These could be other things, could be input or output, but we'll look at building a register. And so a register, basically, what we're trying to build is something that has 8 inputs connecting to our bus that can store a value. So there's some 8-bit value stored in here, a series of ones and zeros, and it's connected and it can send that value out to the bus when the enable input is high. So there's an enable and a load control input here, and normally the enable input would be low, and so whatever value is stored in here is not going to be output to the bus. So it could be some series of zeros and ones, and we're not going to be outputting a 0 or a 1. We're essentially going to be disconnected, essentially, because we're not outputting a 0 in the sense that we're not syncing current, and we're not outputting ones in the sense that we're not sourcing current. We're essentially just appearing to be disconnected from the bus. So if we're not enabled, other modules can communicate, and this module here is not going to interfere. But when this enable line does go high, then whatever value, whatever series of ones and zeros are stored in this register will be output on the bus. And any of these modules on their inputs should see that same series of ones and zeros and could choose to load that value into their own storage. So this register here, for example, has this load input. And if normally that load input would be low, but when it goes high, then what happens is this module here is going to latch whatever value it sees on the bus, it'll store that. And it uses a clock input to do that, so we can coordinate the timing. And what happens is, once that load input goes high, then the next time the clock transitions from low to high on that rising edge, then whatever value is on the bus gets stored in C. And then the load input can go low, and other things can happen on the bus, doesn't matter. We now have that value stored in C, and so we've essentially transferred the value from A to C. And so A can take on another value, other things can happen on the bus. C is going to remember that value. And then it can be enabled, and it can put that value back on the bus at a later time or whatever needs to be done. So what we're looking to do is we're looking to build something that can store a value when on the clock rising edge, only when the load is enabled, and then hold on to that value and then output it to the bus whenever the enable input goes high. So if you've watched my videos on the D flip-flop, you might think, well, that's a pretty good candidate for something to use. And if you haven't watched my videos on a D flip-flop, I would suggest going back and taking a look at those if you don't already have some idea of how a D flip-flop works. But just as a reminder, the D flip-flop has a D input, and it also has a clock input, and it uses this edge detection so that on the rising edge of that clock, when that clock transitions from low to high, at that instant that it transitions from low to high, it stores whatever value is coming in the D input, whether it's a 0 or a 1, it stores it in the latch, and then that output is available at the Q output. So you might think, well, we can use just a series of these D flip-flops to build a register. So we have, however many we need. We're building an 8-bit computer, so we have 8 of them, and have those inputs, and then just tie all these clocks together, and somehow that might work. But the problem with that is we need to have some mechanism to not just always store whatever's coming in, because these D inputs are going to be connected to our bus, and the value on the bus is going to be constantly changing. We only want to store the value on the bus in the register, essentially when we're told to, using that load. Remember, we've got the load input, so we only want to load what's on the bus when this load input is high. Otherwise, we want to keep what is in here stored in here. So what we can do is add a little bit of extra logic around our D flip-flops to kind of control how the clocking is worked. So we still have our clock coming in here, and this is going to be our master clock for the computer that everything is connected to. That clock is coming in here. But what we have is we have our load input over here. And our load input goes through some logic here that controls whether we actually are loading a new value into the D flip-flop or whether we're loading the value that is already in it back into it, which is essentially doing nothing. And so normally if this load is low, let's say it's low in this case, then we're going to have it coming in over here. We're going to have a 0 down here, and we're going to have a 1 over here. And so, we're looking at this coming in through this AND gate, so we have a 0 and something else. Well, it doesn't really matter what this is. If we have 1 0 coming in here, we know the output's going to be a 0, right? Because if it's 0 and 0, that output's going to be 0. If it's 0 and 1, then the output's still going to be 0. So we know that's a 0. Here, we're inverting that 0, and we get a 1 over here. And so in that case, we know that 1 and 1 is going to be a 1 over here. 1 and 0 is going to be a 0 over here. So whatever this is, we'll call it x, we're going to get the same thing out over here. So this same value is just going to pass through. So this AND gate essentially is going to appear to be transparent. So now we have OR, we have an OR gate here, so we're saying 0 or whatever x is. Well, that's just going to be whatever x is. So x, that's what's being fed out of the D flip-flop, right? So whatever's stored in the flip-flop is just getting put right back in the input. And so whenever this clock transitions from low to high, the D latch essentially just latches in the same value that it has, and nothing changes. And that's because our load is 0. Now let's imagine a scenario where our load is goes to a 1. So we have a high value coming into our load input. So in this case, this second case is the exact same circuit, so I'll just draw it down here so you see what's going on. So this is a 1 now. So we have a 1 here, we have a 0 here, right? We're inverting that. And so now, this value that's coming in here, we'll call it x, whatever that is. Doesn't matter what it is because we're anding it with 0, so we know we're going to get a 0, right? Since x is 1, 0 and 1 is still 0, 0 and 0 is 0, doesn't matter. So this is a 0. But down here, we have a 1 and whatever's coming in our input. This is coming in from our bus. So these D1, D2, D3 could keep going for however many bits we have. We have 8 bits, so there's going to be 8 of these things. So that input from the bus is going to come in. So whatever that is, we'll call it y. And if we and that with a 1, then we just get y coming out. And then of course, if we OR that with a 0, we get y coming out of our OR gate. And so in this case, when our load goes high, when it goes to a 1, then when we get a clock pulse here, instead of storing the same thing that was in the flip-flop, we store the thing that is coming in on the bus. And that's exactly what we want. We want to load, when load is high, we want to load the thing that's on the bus. And then that latches it into this flip-flop, and we've now stored it. And now that new value will be the output of this Q output. So this will now be y. That'll be latched in there. So if we want to, we can go ahead and build this. And this is actually this circuit here is built here. And I've used 4 chips here, and just so you know what they are, I've got this is a 7474, 74 LS74, and that is basically has 2 D flip-flops built into it. And so this is the data sheet for it, the 74 LS74, and you can see it's got 2 D flip-flops built into it. And we're using this one over here that's sort of these pins on the bottom. And so you can see it has the D input here. You can see it has a clock. It goes over here to the clock input. You can see it has the Q output over here. And it has our inverted Q here as well. And it also has a couple other nice things. It has a clear pin, so regardless of the clock input and everything else, you can, if you take this clear pin low, then it just resets the flip-flop to 0, or regardless of whatever else is going on, it's kind of an override. And then there's also a preset pin, which is that it sets the flip-flop to 1. So we're not going to use those necessarily, but that's what the pins are. So we've got that here. This is a 7474. And of course you could, in the previous video, I built a D flip-flop from discrete logic gates, and we could do that if we wanted to. But in this case, since I've already got those videos, hopefully you can watch those and know how this works inside. So we're going to take a shortcut and just use that here. And then I've got an inverter. This is a 74 LS04 inverter. I've got some AND gates. This is a 74 LS08. It's got 4 AND gates on it. We're using 2 of them here. And then the 74 LS32, which is the OR gate. And so we're using 1 inverter, we're using 2 AND gates, we're using an OR gate, and we're using, in this case, I just have one of the 74 LS74, one of the D flip-flops on this chip wired up. And so what's going on here is we've got our load input. That's this yellow wire here. And so we have that load input going into one AND gate, and then we have the inverted version of that load input going into the other AND gate. And so the one AND gate that's going into the other input of that is our connection to our bus. This is our data input here. And so that's going into the same AND gate as the non-inverted load. So you can see that. It's going into the same AND gate here. And then the output of that AND gate, this third pin, is the output of the AND gate. That goes over to one of the inputs of our OR gate. Right, and that comes over to one of the inputs of the OR gate. The inverted load is this, comes out of the second pin of our inverter, and that goes over into the other AND gate here. That's right here. And then the input, the other input of that is this green wire here at the top that is coming from the output of our flip-flop, the Q pin, I guess, of our flip-flop. And we also have the LED hooked up to the output there, so we can see what the output is. And so the output of that other AND gate is here. It's this pin, and that is going over to the second input of our OR gate. So our OR gate's got both of our AND gates connected to it. Those are these 2 wires here. The outputs of the 2 AND gates going into the 2 inputs of the OR gate, and then the output of the OR gate comes over here to the D input of our flip-flop. And then this white wire here is just a clock for the flip-flop, so we'll hook that up to a clock here. And then, of course, the output over here I mentioned before, we've got the LED hook there so we can see what it is, and of course it's also going back around to our input here. That's this longer green wire. So we can hook this up and see what happens, and it looks like it appears to be nothing, but I guess there's a 0 stored here in our register. I guess this is a 1-bit register, I suppose. So what we can do is we can set our load to low, and then our input, we can set that as a low or high. Let's set it to high. So we can see that right now, the bus can be low, high. It doesn't really matter. The state of our register doesn't change. And then our clock input, we can hook to a clock. And conveniently, we built one of those in a previous video. So I'm going to hook this clock that we built up here. So just connecting the power across here. So now our clock is powered, and so we can manually advance our clock, or we can turn this on, and we get a nice slow clock. And so I'll hook our clock up there. Okay, so we've got our clock hooked up, we've got our input, and so now our input can be high or low, and actually I'll let the clock run. So when it's low, you see nothing's changing. When it's high, nothing's changing, and that's because we haven't enabled it. So if we've got it high now, and we enable it, we see that with the clock rising edge, it stores that 1. And now if we disable it, the bus is free to change to a 0, to a 1. It doesn't matter, we've now stored that 1 in here, in our register. And now, the bus is a 0. Again, if we enable, or if we load, I should say, this is our load input. If our load input goes high, you see it stores that 1 that's on the button.
Latch on top of a latch.
Of course, now if the bus is changing, it's going to pick up that new value because we still have our load high. But normally the load is going to go high just for one clock cycle, or one clock, I should say. And so this appears to be working. It seems to be doing everything that we need our register to do, with one exception, which is that we have our output here, but of course, one other thing that we need our register to do is not always send its output back, right? So if we just hooked the output of this back to the bus, we'd be constantly forcing the bus to either be a 0 or a 1, whatever this register is set to. So we'd like to add a tri-state buffer or something here, so that we can use that tri-state function of the buffer to turn off the connection to the bus. And so the chip that I'd like to use for that is the 74LS245, and you can see it's got a bunch of these tri-state buffers. So there's a lot going on in here. I know it's a little bit complex, but if we just kind of look at if we just look at this side here, what you'll see is we have an input here coming in on pin 9, and it's connected to a tri-state buffer that then has its output connected to pin 11. And so you can see we can use this tri-state buffer to sort of connect and disconnect data flowing in this direction. You notice there's also a buffer flowing in the other direction, which can be convenient for connecting to a bus, and that's why this chip is considered a bus transceiver. It is useful for interfacing with a bus and sending data in both directions. And there's a pin 1 here is a direction control, and you can see that it's hooked up to a couple gates here that essentially control, whether the bottom row of tri-state buffers is on, in other words, data is going this direction, or whether the top row is on and data is going this direction. In our case, we only want data to flow in one direction because we've already got the load function here worked out, so we really just need the tri-state buffer on the output. And so for that, we can essentially just tie this direction input to a high value, to 5 volts, and that'll force it to always go this direction. And then we have an enable pin here that we can just use to turn on or turn off all of these all at once. So this is a good chip to use as our buffer. So we could add this to our circuit here that we have, and then of course we would need to essentially build 8 copies of this. And there's room on some of these chips, but it would still take a fair amount of room to do that. And so this is where we kind of come to we have a decision to make, I guess, which is what is it that we're trying to build here? What is it we're trying to do? I mean, we could approach this and say, our goal is to build a computer using only basic logic gates, and maybe we want to build our register using this. In fact, maybe we don't even want to use the 74LS74 as our D flip-flop, and we actually want to build a D flip-flop from AND gates and OR gates, like we have in previous videos. And that could be a goal. You could choose to build a computer that is just AND gates and OR gates and inverters and that sort of thing. My goal with this, I think, is more to learn a bit about building the computer and how the computer works, and have a project that you can do kind of in your spare time over a couple of weeks, and not be so hardcore that we only are going to use AND gates and that sort of thing. And so actually, what I'm going to do for the registers is actually something even simpler than this, which is the 74LS173 is a chip that is a 4-bit D-type register, and so it is actually designed to be used as a register. And so what you'll see here is you'll see that this 74LS173 has 4, doesn't quite fit here, but it's got 4 D flip-flops in it, and it has this same logic that we've been looking at. It has the output coming back around into an AND gate, and then 2 AND gates going into our inverter, and you can see the input is going into the other AND gate, and then you can see the other sides of these AND gates are connected to either side of an inverter that goes to our, they're calling it the enable, to sort of our load inputs. That's a little bit weird. They have 2 of them and they're inverted. I'm not really sure why they did that. It's a little bit less convenient for what we need, but definitely more convenient that all of this is built into one chip. So I'm gonna use this chip. The other nice thing about this, sort of nice maybe, is it also has tri-state outputs, and then it has an output control. And again, they have 2 of them and they're inverted. I'm not really sure why, but they have this output control that we can use to turn on or turn off this output. So you do have a choice of whether you want to use the 74LS173, which gives you a lot of the functionality in one chip, or whether you want to, kind of go extreme and try to build it out of discrete logic gates. It's up to you. For my money, I say, use this. I think in the computer that I'm going to build here, we're going to use maybe 10 or 12 of these chips of the 74LS173s. And so if you were trying to implement that with discrete gates, I mean, you could do it, and maybe, I don't know, maybe you enjoy that challenge. But I think there's enough other challenge in building this computer that I think it's perfectly fine to take a little shortcut and use a pre-built register like this. So in the next video, we'll go ahead and use the 74LS173s and build a couple of the registers that we're going to use for the computer and go through testing them. So in the last video, we took a look at building registers. We actually built a register, well, a 1-bit register anyway, using somewhat discrete logic here. We did use a D flip-flop. But then I also talked about the 74LS173, which is basically a 4-bit register on a chip, and how we're going to use that. One thing that I don't like about using just the 74LS173 is that it does have its own output control, which means that once it stores some series of bits here in these latches or these flip-flops, you can't see what is in it, and I think it's pretty important for this computer, because this computer is designed as something that you can use to learn about how computers operate, and I think it's pretty important to be able to see what's in every register. So what I'm going to do is I'm going to use the 74LS173 register chip, but I'm going to tie the output control such that the output is always on. But of course, you don't want the output to always be on, otherwise the output will always be outputting something to the bus. And you don't want that because then that register is putting its data on the bus all the time, and that defeats the purpose. You want to have that enable ability. And so what I'm going to do is I'm going to have the output always on, so that we can hook LEDs up to this output. But then on the other side of those LEDs, I'm going to use something like the 74LS245, which has these tri-state buffers in it. That way we can use the 74LS245 to control what's going out on the bus. So have the 74LS173 register always on, so we can see the LEDs to tell us what's in the register, but then use this to control whether it's actually being output to the bus or not. So essentially, that kind of looks like this. This is sort of what that circuit would look like. Hopefully this makes some sense. But that's sort of what that circuit would look like. Hopefully this makes some sense. But I've got the 74LS173, and each one has 4 bits, a 4-bit register, so I'm using 2 of them to cover our 8 bits. So we have our 8 bits coming in. And then I have the output, so M and N. I'm not sure why they call them that, but those are the output controls, and for some reason there's 2 of them. But in any event, if you tie both bits into ground, then the output will always be on. And so these will always be outputting, which is what we want. And then I have the 8 LEDs hooked up, so we can see what's stored in these registers. So the output's always on, and you can always see on these LEDs what's actually stored in those registers. You can ignore this line, I needed to draw this bigger than I thought. And then we're using the 74LS245 to actually control whether it goes back out on the bus or not. And so there's an enable line that the 74LS245 has, and it's an inverted logic line, so it would normally be high, and then you bring it low to enable it. And then when you bring that low, then we'll see whatever this is will actually get output. But if the enable is high, meaning it's not enabled, then this is simply shut off, and it's not outputting a 0 or a 1 to the bus. So it's fairly simple. We've got 8 connections to the bus as inputs. We've got 8 connections to the bus over here as outputs. We've got our load signal coming in, which is connected to the 2 load pins on each of the 74LS173s. And again, this is inverse logic, so when you bring it low, that tells these to load the value from the bus. We've got the clock, which I don't think I drew, but the clock would be pin 7 on both of these 74LS173s. So you need to tie pin 7 together and then connect that to your clock. I did draw pin 15 here, which is the clear line, which we're not going to use yet, but eventually, when we get the rest of the computer built, we'll want to tie all these clear lines together so you can have a button somewhere to just clear everything in the computer, which can be helpful. And I think that's pretty much it. Yeah, there's the direction here, which we're just tying to 5 volts, so that the direction is always in this direction from this side to this side. So I've started to build this here. So these are the 2 74LS173s. These are our register chips, and then of course our 245 74LS245 over here, which is we're essentially using as the output buffer. And I've got some LEDs hooked up here, just kind of stuck in here on the outputs. So you can see pin 3, 4, 5, and 6 is connected here. Pin 3, 4, 5, and 6. I've got the LEDs there. Same thing over here. Pins 1 and 2, as you can see here, tied to ground, and that just enables our output all the time. So we'll always see the output on those LEDs. Pin 7, which I didn't draw here, is the clock, and you can see I just tied those together. Pin 7 on both of these with this white wire, and then we'll have to connect that off to our clock, which is going to be elsewhere in the computer. The clear signal is pin 15, so I've just tied the pin 15s of each chip together. And then our load here is pins 9 and 10 on both chips. And so you can see 9 and 10, 9 and 10 tied together. So those are just all tied together, and then we'll just need to connect our load signal to here somewhere. So now all that's left to hook up here is connecting the outputs of the 74LS173s, which of course are already connected to these LEDs, which are just connected across to ground. You can see that here, but they're just connected across here to ground. And we just need to connect those as well to our 74LS245, so just connecting these across. And conveniently, all of these pins are on the same side here. So 1, 2, 3, and 4 are kind of on the bottom side of this chip here, and the inputs for the 74LS245 are 2, 3, 4, 5, 6, 7, 8, 9, and those are all down here at the bottom of this chip. And actually, one of the reasons I'm using the 245 specifically is because of that. It just makes the wiring easier, because you can set the direction as one direction or the other. So you might wonder, if you're wondering why we're using this bidirectional chip, but then only using it in one direction, it's actually just because it makes the wiring easier, and it doesn't cost any more than any of the other chips. So I'm just going to go ahead and hook this up. You just have to be careful to squeeze all this in here. It can be a bit of a tight squeeze. And of course, you are under no obligation to make your board look as pretty as mine. I'm just trying to make this easy for you guys to see what's going on. But certainly no one is going to hold it against you if you've got a big old tangled mess of wires. And now I'm starting to cover up this black wire under here, which is why I wanted to show you everything else before I stuck the rest of this in here, because it does kind of mask what's going on underneath. But there we go. We've got this hooked up now, so that all of our outputs all of our outputs here from the 74LS173 register chips are hooked to the 8 inputs across our 74LS245, which is over here. So the other thing we can do, or that we should do, is tie the bus sort of terminals here together, right? So each of these 74LS173s has 4 connections to the bus, and so across both of them there's 8 connections to the bus. And then the 74LS245 buffer here also has 8 connections to the bus. And we can actually just tie those together directly here, and then coming off of this board we'll just have one set of connections. And it might feel kind of weird to tie your outputs back to your inputs, but remember, we've got our load and our enable signals, and we're only going to be doing one or the other, right? So really, this is only sometimes an output, and this is only sometimes an input. And if we're doing things right, they're never an input and an output at the same time. So connecting them to each other, it might seem strange to connect the input to the output, but it's actually okay. Okay, and that's pretty much it. And so the connection to our bus is these eight blue wires, or sort of this side up here. So we want to just add these connections here that we can connect to a bus. Let's do that. And so these 8 wires here are our connection to our bus. So we've got our load signal over here. We've got the enable over here, which is the enable for the output to the bus. And of course we've got the reset here as well, which is this pin 15, which we'll just tie that to ground. We're not going to use that. We'll just leave that so that it's not resetting everything. And then the last thing we have is the clock, which is right here. There's this white wire connecting here. And so that's it. That's pretty much our register. So our register has all these connections. And so in order to test it, we've got to connect some stuff up to it and kind of play with it and see if it behaves the way that we think it will. So what I'm going to do is I'm going to use another breadboard just with 8 LEDs on it and use this to kind of see what our bus is doing. So what I'll do is I'll hook the bus connections up to these LEDs. And of course we want to make sure they're connected up in order. And so now our 8 bus connections are connected up to these 8 LEDs, and they're connected in order here, so we can see what our bus is doing. And of course, we also want to connect the ground of these LEDs over to our board here, so we have a common ground, so that our LEDs will work. And so now we should be able to power this up and see what it does. So I'll connect our power in here, and it looks like everything is all zeros, which is, I don't know, maybe interesting. These are D flip-flops here, so they could start in either state. So some of yours might start on, might start off. We don't know. I'll set the enable to high, and I'll set the load as high as well, because these are these sort of inverse signals. Remember, so they're inverted. So setting enable to high means we're not enabled, and setting load high means we're not loading. And then we'll bring them low to actually turn those signals on. Then the last thing we have is our clock here, and I'm going to hook that up to our clock circuit that we built in the previous video. So we'll just hook the clock up just like that, and then I also want to hook the power connections from our clock up to this board, so we're powering our clock. And there we go. Now our clock is flashing away there. And so now we can start to test this. And so the first thing I'm going to do is I'm going to see what happens when we bring our load pin from high to low. So in other words, we're telling our register to go ahead and load whatever's on the bus. And now there's nothing connected to the bus, and so it'll be sort of interesting to see what happens here. So if we bring that low, we see that when the next time the clock went high, all of our bits in our register went high. And you might wonder, well, why is that happening? There's nothing on our bus. These are all off. Why would these come on? Well, because there's nothing on the bus at all. These pins aren't high or low. There's nothing driving our bus. There's no inputs here. This is the registers are going to default. Any TTL chip typically will default to a high input. If you don't connect the input, it defaults to high because there's typically a pull-up resistor inside the chip there on the input. And so that's just what we're seeing. Is we're seeing that since there's nothing connected, they just show up as high. But what we can do is we can now take our load pin and bring that high again, which turns the load off. And now we can take our enable and see what happens when we enable this by bringing enable from high to low. And we see when we bring that low, we see the output. So we have all ones stored in our register, and when we enable the register, we can see that enabling it outputs the contents of the register to the bus, which is exactly what we want the enable to do. Now we can try something else. We can try inputting a value, and the way we can do that is, we saw that by default we're getting ones. So what we could do is we could just connect some of these bits here to ground, and that'll I don't know, connect these bits here, and maybe we'll do one more. We just connect this bit over here to ground. And now, if we try to load what's on the bus, we should see 3 of these turn off. And indeed we do. And so now we have that value on the bus. And so now if we change that value so these aren't, we're still loading. That's why, yeah. So we're still loading. So it pulled in that new value when I disconnected these. So let me reconnect these. Normally the load would only be active for one clock tick. So the load is active, and then the load goes inactive, so we take it high. And so now we can change what's on the bus, and we store that value in the register, which is what the register should be doing. And then if the register needs to output that back to the bus, we can use the enable to do that, and we get that same value back out on the bus. So it looks like our register is working. Now, where things get interesting is when we have multiple registers, and in fact, for our computer, we're going to need to build a couple registers. So here I've got a second register built exactly the same way as the first one, and we can hook it up to the bus as well. So I'm going to disable that bus, and I'm going to hook the second register up to the bus in the same way. So we've got both registers now hooked to the bus, and of course we'll want to make sure we connect our power here as well. So let me connect our power rails here, and then we'll connect the two boards here so that we've got power going everywhere that it needs to go. So we've got our power hooked up to everything. So now we have two registers. And so this is actually kind of interesting because now we have a value in this register and we have another value in this register down here. This is this value that we stored there before, and this is just all zeros. Oh, and of course we want to hook our clock from our second register up to our main clock here. We got our clocks hooked up, everything's hooked up. So now what we can do is we could actually do a register transfer. We could enable the top register, and that puts the value out on the bus, and then we could load into our second register. And then boom, on the next clock cycle, we load that down here, and then we can turn that off, and we can turn off our top register, and now both of these have
Oh.
Have this value stored in them, and then now the bottom register could output that to the bus, and then some other register could read it, or the top register could read it again. And so now we've got two registers here connected to the common bus. Either of them can output their value to the bus, either of them can read a value from the bus. So now in total for our computer, we're going to need to actually build three registers for the computer. So we've got the A register, the B register, which are just like this, and then we also need to build an instruction register, which is very similar. There's a couple differences with it. One is I've just basically built it the opposite direction, and that's just because physically the way that we're going to lay out all of the boards, we're going to put the bus in the middle, and it's just easier if the 74LS245 chip, this buffer chip, is towards the middle of the board. And so these are going to be on the right side, this is going to be on the left side, and so just having this kind of reversed is a little bit easier. And so you can see these are basically, if you look at the A and the B registers that we built here, they're mirror images of the instruction register, which is this board down here. Otherwise, it's pretty much identical, except for one other change, which is that the most significant 4 bits, so these top 4 bits, are a little bit different in that they are not output back onto the bus. And so you'll see here, there's only 4 green wires, so only the least significant green wires are connected to the LS245. And so if we look back here, that's just, these 4 wires for the most significant, they just aren't connected. And the reason for that is that rather than being output back to the bus, they're going to go into the instruction decoder, and we'll get into that in future videos. But for the instruction register, only 4 of the bits are going to be output when we enable it. But otherwise, it's pretty much the same. So again, we can hook this up as well. So we've got the power here. I can hook that over to the power for everything else. So that's that. And then, of course, I can hook the bus up to our common bus here. And there we are. So our bus is hooked up. Power's hooked up. Oh, we do need clock. Make sure that's hooked up. So our clock is here. And that should hook up to our, no, it doesn't quite reach, but that's okay. We can just connect it over here, as long as all of our clocks are connected. There's these white wires. So our clock's connected, everything's connected. So what we could do is we could go ahead and output one of these registers. Let's take the B register, and we can output that. And then we want to input that over here on our instruction register, let's say. So let's see which one of these, this would be the load. So if we take that low on the next clock cycle, yep, we've now inputted that value. And so now we can stop outputting that. Oh, right. Gotta make sure once we read it in that we are no longer loading. And now it's safe to take that off the bus, and it'll stay there. And so now we have that in there. Now, remember the one difference here is we don't have these top 4 bits hooked up, the blue LEDs. That's why I did them different colors, is they're a little bit different. The blue LEDs aren't hooked up to the output. So if we enable like this, we see only the lowest 4 LEDs come on because the blue ones aren't hooked up. These blue LEDs are going to be hooked to another part of the computer for the instruction decoder, because this is the instruction register, and these four bits are going to have the instruction. They're going to go to the instruction encoder. These 4 bits are typically used for an address or something, and they can go back out on the bus. Don't worry if none of that makes sense. The point is we just don't want to connect these top 4 bits for one of our registers here. And so if we want, we could, if we read this back in to somewhere else, let's say we load this into the A register now, we end up with that same value there. And then we can stop loading that in the A register, and then we can stop outputting that on the bus, and so now there's nothing on the bus. And so now, we could load this from the A register to the B register. We output it on the A register, it goes out to the bus, and on the B register, we change our load pin here, and it loads it in there. And so you can see we're getting these bus transfers. Each of our registers, it appears, is able to output to the bus, and each of the registers is able to input something from the bus. So it looks like we've got our 3 registers built: the A register, the B register, and the instruction register. You might already be familiar with binary. For example, this is 101 is equivalent to 5 in decimal. That's because this is the 1's place, this is the 2's place, 4's place, 8's place, 16's, 32's, 64's, and 128's. And we have a 1 in the 4's place and a 1 in the 1's place. 4 plus 1 is 5. So this is fine, but how might we represent a negative number? So let's say we wanted to represent negative 5. Well, there's a couple ways we can do that. One way is to take this 128's place, and instead of using that as the 128's place, use that as a sign. So change this to a 1 here to indicate that this is negative, and then the rest of it is the same. 1, 0, 1. And so this would be 5 here, and then instead of this representing 128, it represents that the number is negative, so negative 5. Now, of course, it's important to know how many bits you're working with, right? Because if we're only using 4 bits, then a 5 would be 0, 1, 0, 1. That's equal to 5. But then we're going to use this top bit here. In this case, we're only using 4 bits. So the top bit is this 4th bit, and so negative 5 might be a 1, 1, 0, 1. And now instead of this being the 8's place, this is actually representing the sign. So this would be negative 5, and this would be 5. So it's important to know how many bits you're working with so that you know which bit is the first bit, and therefore which bit indicates what the sign of the number is. So to keep going with this example, we can look at just regular counting in binary here. Of course, if we have all zeros, 0, 0, 0, 0, that's equal to 0. And then if we have a 1 in the 1's place, that's equal to 1. A 1 in 2's place, that's equal to 2. A 2 and a 1, that's equal to 3. And then, of course, a 4 is 4. A 4 and a 1 is 5. A 4 and a 2 is 6. A 4 and a 2 plus a 1 is 7. So that's simple enough. And then if this first bit here is indicating our negative sign, then we can go backwards too. So if we have a negative 1, that's negative 1. A negative 2. A negative, 2 and a 1 is 3. And then negative 3. Negative 4. Negative, 4 and a 1 is 5. With a negative is negative 5. 4 and a 2 is 6, so this is negative 6. And then a 4 plus 2 plus 1 is 7, and that's a negative 7. So this is our sign bit. So this first bit is our sign bit, and then these other bits are just our 1, 2, and 4 place. Simple enough. A couple weird things about this, though. One is that you notice there's a negative 0, right? Because you can have 0, 0, 0, and then it can either be a 0 in the sign bit place or a 1 in the sign bit place. So you can have, there's a difference between 0 and negative 0. So that's kind of weird. The other thing that is maybe a little bit inconvenient, we'll look at some other approaches that don't have this problem, is if you try to add these things together, things get kind of weird. So let's say we want to add a 5 and a negative 5. So normally 5 plus negative 5, you would expect to get 0. Simple enough. But here if we look at 5, 0, 1, 0, 1, and negative 5 is 1, 1, 0, 1. If we add these together, 1 plus 1 is 2, which would be a 0 and then carry the 1. 1 plus 0 is 1. 1 plus 1 again is 2, but we'll put that as a 0 and carry the 1. And then here 1 plus 1 again is 2, so a 0 and carry the 1. So in this case, what we're seeing is 5 plus a negative 5 is not 0, it's 0, 0, 1, 0, which, well, and we have a carry. So we have a carry coming out of this 1 bit that we don't, if we're working with 4 bits, we're going to ignore this carry bit. And so we have 0, 0, 1, 0, which is 2. So that's kind of weird. If we're adding 5 and negative 5, we wouldn't expect to get 2. And you can try adding some other things here. It doesn't work. So let's take a look at another scenario here. This is called 1's complement. What this is again, everything from 0 to 7 is the same. Same as we saw before. And this first bit here is all zeros, so we know that these are all positive. But what we do for the negative numbers is we actually just flip all of the bits. We take the complement of all of the bits. So 2 here is 0, 1, 0. Well, 0, 0, 1, 0. Negative 2 is 1, 1, 0, 1. So we're just flipping each of those bits. So we flip the 0 for a 1, we flip the 1 for a 0, we flip the 0 for a 1, and so on. If you look at each of these numbers, so 5 is 0, 1, 0, 1, negative 5 is 1, 0, 1, 0. So what happens with this? So we still have this kind of strange thing where we have negative 0, and we'll come back to that in a minute. But what we can do is we can try to add some numbers. So if we add 5, so 0, 1, 0, 1, so that's 5, and negative 5, 1, 0, 1, 0, we add those, adding negative 5 here. What we end up getting is 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 0 is 1, 0 plus 1 is 1. We get 1, 1, 1, 1, which is negative 0. So that's closer, right? 5 minus 5, you expect to get 0. Negative 0 is, I guess, the same thing. So that's pretty good. And that actually works for any of these. We can do 3 minus 3, or 3. So 3 is 0, 0, 1, 1. Negative 3 is 1, 1, 0, 0. So this is 3 plus negative 3. If we add these together, so 1 plus 0 is 1, 1 plus 0 is 1, 0 plus 1 is 1, 0 plus 1 is 1, we get 1, 1, 1, 1 again. And so again, 3 minus 3 is negative 0. So this is definitely doing a lot better than here, where we were saying 5 minus 5 was 2. That's definitely not right. So negative 0, definitely a lot closer. Let's try some other things, kind of see if we can see a pattern here. So if we did, let's say 5 plus negative 3. So 5 minus 3, let's see what we get there. 5 is 0, 1, 0, 1. And negative 3 is 1, 1, 0, 0. So 1 plus 0 is 1, 0 plus 0 is 0. 1 plus 1 is 2, so we'll put a 0 and carry a 1. And then 1 plus 1 again is 2, so we'll put a 0 and carry a 1. And so if we ignore this first bit here, because we're working with 4 bits, we get 1. So 5 minus 3 is 1. That's close. It should be 2, but let's see what happens if we do, let's say 6 minus 2, or 6 plus negative 2. So 6 is 0, 1, 1, 0. Negative 2 is 1, 1, 0, 1. 1, 1, 0, 1. 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 2, put a 0 and carry the 1, 1 plus 1 is 2, put a 0 and carry the 1. Again, ignore that first bit, because we're working with 4 bits, so 0, 0, 1, 1 is 3. So we're saying 6 minus 2 is 3. Close, but we're definitely seeing an interesting pattern here. In fact, if we look, these places where we're getting this negative 0, if we just go down 1, we see 0, which is what we want. Here, 5 minus 3, we'd expect to see 2, but we're seeing 1. So if we just go down 1, we'd actually see a 2. 6 minus 2, we'd expect to see 4, but we're actually getting 3. But if we go down 1, we get the right answer. So we could just always add 1 to each of these. Of course, it's kind of weird to say add 1 to negative 0 to get to 0, but if you kind of bear with me a minute, you'll see that if we add 1 to the binary value and it flips over, you do get to the right thing. And here you get to the right thing. So the 1's complement, just flipping all of these bits, is close. It's very close. It's off by 1 on all of our arithmetic, and it also still has that nice property that we saw with the sign bit, which is you can look at this first bit and you can tell these are all negative numbers, and if the first bit is 0, then they're positive numbers. So it seems like the 1's complement has a lot of the a lot of nice properties that you'd have in the sign bit. The one thing that's well, I guess it's not too bad, is that to invert or to negate a number, if you're going from 5 to negative 5 with a sign bit, all you have to do is flip 1 bit. You just flip that first bit to a 1 and you get to negative 5. With the 1's complement, you have to invert each bit. So it's a little bit more work, but of course inverting bits is pretty easy to do in hardware. If we're building hardware to do this, if we're building a computer, going to be doing some math. So 1's complement seems pretty good, but it is off by 1. So what we can do is look at another scenario, which is 2's complement. And if we compare 1's complement to 2's complement, it's basically the same, except what it does is it gets rid of this negative 0. So instead of having negative 0, we just go right to negative 1. Negative 2, 3, 4, 5, 6, 7. And the kind of weird thing here is we have a negative 8, and we don't have an 8. But the nice property about this is that all of our math works out very nicely. So if we have 5 minus 5, 5 here is 0, 1, 0, 1. And so that's 5. And negative 5 is 1, 0, 1, 1. So 1, 0, 1, 1. And if we add these things, if we add negative 5, 1 plus 1 is 2, so we'll put a 0 and carry the 1. 1 plus 1 is 2, put a 0 and carry the 1. 1 plus 1 is 2, so we'll put a 0 and carry the 1. And 1 plus 1 is 2, so put a 0 and we have a 1 that we're carrying. And so you'll notice that each, when we're looking at the negated version of something, when we add each of these place values, we get a 2 each time, and that's why it's called 2's complement. But in any event, you see that we end up with 0, which is just what we would want when we add a number to its inverse. And in fact, you can try it with any of these numbers, and you'll find out that you get all zeros. So let's try, 6 minus 2. So 6 is 0, 1, 1, 0. That's 6. And minus 2 is 1, 1, 1, 0. 1, 1, 1, 0. And if we add these together, so we add our negative 2. Oops, negative 2. Adding negative 2 there. 0 plus 0 is 0. 1 plus 1 is 2. So we'll put a 0 and carry the 1. 1 plus 1 plus 1 is 3. So it's a 1 and a carry a 1. And the 1 plus 1 is 2. So 0 and carry a 1. And again, we ignore that fifth bit there. And so 0, 1, 0, 0 is 4. And sure enough, 6 minus 2 should be equal to 4. So this 2's complement works pretty well. And it also has this nice property again, that first bit is a sign bit, right? Because all of these negative numbers have a 1 there. And what's even more interesting about 2's complement is if you look at the place values, it actually makes sense. This is our 1's place, this is our 2's place, this is our 4's place. And this place here, it's, it looks like a sign bit, but really it's a negative 8's place. And you can see when we have a negative 8 and all zeros, we have a negative 8. But if you have a negative 8 and a 1, you get negative 7, right? If you have negative 8 and a 4, you get negative 4. If you get negative 8 plus 4 plus 2 plus 1, you end up at negative 1. So this bit value actually has a mathematical meaning, which is why our math works out. So it's pretty cool. The one thing that's a little bit harder with 2's complement is negating a number. So if we want to go from a 5 to a negative 5, it's kind of a two-step process, right? So 5 is 0, 1, 0, 1. The first thing you have to do is take the 1's complement, 1, 0, 1, 0, so flip all the bits. So you're just inverting everything. That's easy enough. But then you have to add 1. So you invert, and then add 1. So to add 1 to 0, 1, 0, 1 is just 1, 0, 1, 1. And then this invert, so this is 5, then we invert it, and then we add 1, and that gets us to negative 5. You can see negative 5, 1, 0, 1, 1, 1, 0, 1, 1. So it's a little bit more work to go from a positive number to its inverse, because you have to invert it and then add 1. But what you'll see in the next video when we build a circuit that can add and subtract, you'll see that it's actually not too hard to build this in hardware. So in our previous videos, we built these registers that are able to store a value. So for example, this register currently has the value 6 in it, 1, 1, 0 in binary is 6. This register currently has a value 2, 1, 0 in binary is a 2. And these registers are connected to a shared bus so that they can output their contents to the bus. If we set this signal here, you can see the 6 gets output to the bus. And they can also